Let's talk about lenses. I want to give you some simple tricks that you can use to always be able to tell the nature of the image that will be formed by a lens depending on the object's position with respect to the lens. Already, there are two, as you may know, there are two broad types of lenses. You have convex lenses, which kind of curved outwards, and you have concave lenses, which kind of curve inwards. So usually the convex lenses are converging, so we usually call them converging lenses, and the concave, we call them divergent or diverging lenses. So in principle, when we want to determine the nature of the image formed by any of the lenses, there are two ways we usually go about that. We can decide to use geometrical constructions. So, geometrical constructions. So the ray diagrams, and there are rules for that. Or we can use the lens equation. So the geometrical constructions are simply based on some rules that we can use to determine the nature of the image that's formed in any case, assuming that rays of light traveling straight lines and are refracted by the lens to a certain point. For example, assume this is a lens. This line is known as the principal axis. No, and here you have the center of the lens, usually known as the pole. So if you have, for example, a ray of light that passes parallel to the principal axis, it's going to be refracted towards the principal focus. See that? If you have another ray of light that passes, so let's say this is f prime. If you have another ray of light that passes through the principal focus, then it's going to be refracted parallel to the principal axis. And the last rule is that if you have a ray of light that passes through the center of the lens, like that, then it's going to be undeviated. So those are the rules you can use, or you can go with the lens equation, usually written as 1 over u plus 1 over v equals 1 over f, where u is the distance of the object from the lens. So if I just make a rough sketch here, let's say this is the object, u is the distance of the object to the lens, v is the distance, let's say the image is formed, I don't know, somewhere here, v is the distance of the image to the lens, and f is just the focal length of the lens, which means the point where all parallel rays converge after passing through the lens. So these are really the two techniques that can be used to determine the nature of an image, really, for any type of lenses. Yeah, but I want to give you a trick that you can really use to always know how what the image looks like, depending really on where it's placed on the principal axis, without you having to go through the geometrical construction techniques or going through the lens equation. So let me just take another sheet of paper. Let's start with convex lenses, which are really usually more common. So let's draw a convex lens on a principal axis. So let's say this is our convex lens. Here you have the object focal point. You have f, you have 2f, and here you have the image focal point f prime and 2f prime. So what you should consider here is the position at which your object is with respect to these reference points. And the main reference point that you should have in mind when dealing with a convex lens is the 2f position. And that's really the first case. So if your object, I'm going to write it here, if your object is at 2f, so this is really your reference point. Let me just put it here, reference. Because when an object is placed at 2f, let's say it's like that, then the image through a convex lens is going to be like this. It's going to be on the other side, and it's going to be the same size as the object. So we call this one-to-one conjugation, which means that the geometry of the object is really maintained. The image has the same size. So here the image has same size as the object, right? And it's also the distance from the object to the lens is equal to the distance of the image with respect to the lens. So the image is the same size and at equal distance to the lens as is the object. So this is really your reference point. You know that if you place an object at 2f, your image is going to be formed at 2f prime. And as you can see, it's going to be inverted as well. So first reference, an object placed at 2f has an image that's formed at 2f prime. The image is the same size as the object. It's at the same distance to the lens as the object is, and it's inverted. Or it's real, if you prefer. Inverted and real. Now, from this reference point, what you should keep in mind is that if you move your object towards the lens, then the image is going to get further from the lens and larger. Hope you can see that. And if you move your object from this reference point away from the lens, the image is going to get closer and smaller. Which means that if your object is at a distance greater than 2f, which means on this side, then you're going to have an image that's going to be diminished in this case, or reduced if you prefer, and it's going to be real as well and inverted. So that's really the trick. Now, if your object, if you now leave from the reference point and you get closer to the length, let's say you're at f, so object at the focal point. So if the object is placed at the focal point, so here, like that, then here you really have another special case because the image is going to be formed at infinity, which means the rays here are going to be parallel in this situation. So we say the image is at infinity. So object at f, image at infinity. Image at infinity, so yeah, the rays are really parallel. And then if you are between the center of the lens and the focal point, so object between the center, let's call that center O, and F. So in this situation, the image, the nature of the image really changes. So if you have your object here, like that, in this case, the image is not going to be real anymore. The image is going to be magnified. It's going to be erect. And it's going to be behind the object. yeah, it's really funny, which means that yeah, and something so virtual. Forgot to mention that. Which means that if your object is here, your image might be formed somewhere here. It's virtual, so I represent it with a dotted line. You can see that. So it's magnified, it's erect, it's virtual, and it's really behind the object. So these are really the simple tricks that you can use in order to know the nature of the image formed by a convex lens. It's really easy. So you start with the reference point, which is 2f. You know that if the object moves away from the lens, then the image gets closer to the lens on the other side and is diminished. On the other hand, if you move closer towards the lens, then your image is going to move away from the lens and get magnified. And then you have a special case at f, where the image is at infinity, and between O and F, where the image is virtual, erect, and magnified. So with this, you would always be able to remember the images formed by convex lenses. Let's move to concave lenses, which is the second case. Concave lens. For a concave lens, it's really easy because you just have one configuration to know. So let's suppose here we have the principal axis. Here you have your biconcave lens. Again, we have the object and the image focal point. So in general, there is just one thing you need to know for a concave lens, just one, which is that no matter where you're going to place your object, let's say you place the object here, okay, no matter where you're going to place your object, the image formed by a concave lens is always going to be diminished, which means it's going to be smaller than the object, like that, okay, and it's going to be in front of the object, on the same side, on the object plane, if you want. Are you seeing that? So this is the object, this is the image. It's diminished, it's virtual, it's erect, and it's on the same side as the object is. So diminished, erect, virtual, yeah, so this is really the only configuration you need to have in mind for a concave lens. So hope this was useful and that it was clear. I remember when I was in college, I used to have a lot of difficulties with these rules, because for a convex lens, there were really so many different situations, but I was not really able to clearly distinguish these different cases. So I hope here it's clear enough. In the next video, we are going to see the tricks that you can use to also deduce or to know the image, the nature of the image formed by, this time, curved mirrors, right? So concave and convex mirrors. If you enjoyed the video, please drop a like, subscribe, and add a comment. I'm always very glad to read you guys. And I see you in the next video. Until then, remember that physics is the belief that a simple and consistent description of nature is possible.